In the last lecture, we were discussing the transition from a laminar to a turbulent flow and the characteristic features of a turbulent flow. As we had discussed, the transition takes place at a Reynolds number that is approximately 2100. Okay. Laminar flow has straight smooth streamlines. The momentum conservation equation we had derived for a laminar flow, where the momentum transport perpendicular to the flow direction, perpendicular to the axis, is only due to molecular diffusion and therefore given by Newton's law for viscosity. This is substituted into the balance equation and we had derived the conservation equation, solved it to get the velocity profile as a parabolic velocity profile with the maximum at the center and 0 velocity at the walls due to the no slip condition. Streamlines are straight and smooth and there is no velocity fluctuation in the cross stream direction. After the transition to turbulence, there is a transition to a different kind of flow profile, more plug like at the center, steeper gradients at the walls. Because the gradients are steeper, the shear stress, which is proportional to the derivative of the velocity at the wall, is much larger. The no slip condition is still satisfied at the wall, both for the average fluid velocity as well as the velocity fluctuations. However, within the fluid there are large velocity fluctuations in both the streamwise and the cross stream directions. At a given location, if you measure the velocity as a function of time, you will find fluctuations in all components of the velocity. These fluid velocity fluctuations transport mass, momentum and energy in the cross stream direction. That mechanism of transport is much more efficient than that for a laminar flow due to molecular diffusion. Due to this, the transport coefficients are much higher. I had given you the friction factor correlation for a laminar for a turbulent flow, the Colebrook correlation, as well as the Moody charts, which basically give you the friction factor as a function of Reynolds number. Okay. We had discussed the transition. Okay. The transition takes place due to an instability to finite amplitude disturbances for a pipe flow. The laminar state is never unstable to infinitesimal disturbances. The laminar state is still stable to infinitesimal disturbances at all Reynolds numbers. However, as the Reynolds number is increased, you get an instability due to a finite amplitude disturbance. That causes a transition to turbulence, and you can increase the transition Reynolds number by making sure that the fluctuations are reduced. Okay, you can damp out disturbances, reduce disturbances in the environment and maintain the flow at in the laminar state at much higher Reynolds numbers. This is in contrast to other kinds of transitions in a channel, for example, or in a Taylor-Couette for a rotating fluid, the Rayleigh-Bénard for a heated fluid. Those transitions are due to infinitesimal disturbances. Okay, the pipe flow is due to a finite amplitude disturbance. So, this is transition in a pipe flow, and we had discussed the general characteristics of turbulent flows. There are large energy fluctuations in all directions. The flow is necessarily 3-dimensional. You cannot have 1-dimensional or even 2-dimensional turbulence. You cannot have velocity fluctuations in either one or even in 2 directions. Velocity fluctuations are necessarily 3-dimensional. They do reduce to 0 at solid walls. Both the mean velocity and the turbulent fluctuations reduce to 0. Because of these fluctuations, there is convective transport. By the mechanism of convective transport by the fluctuations, which is dispersion, is far more efficient than molecular diffusion. Therefore, the transport coefficients and the viscosity, the effective viscosity that you get are much larger than that due to molecular diffusion. There is a range of length and time scales. However, even the smallest scales for the eddies are much larger than the molecular scales. Therefore, turbulence is a flow property, okay. It is a continuum phenomenon, okay, and it takes place primarily at higher Reynolds numbers. So, what are these length and time scales? Let us discuss this a little bit. Okay. Okay, what are the length and time scales of turbulence? If you look at the turbulent flow in a pipe, for example, okay, you will of course have eddies which are comparable to the size of the pipe, okay, large scale, but you will also have a series of smaller and smaller scale eddies, parcels of fluid in correlated motion. Okay. The size of the largest eddies is comparable to the diameter of the pipe, okay, and the time scale of the largest eddies, okay, the size, okay, so okay, the size is the same as the diameter of the pipe, okay, and the time scale is just from dimensional analysis d by v average, okay, and the velocity scale is approximately the average velocity, okay, for the largest scales. Okay. Strain rate, velocity divided by a distance. So, this from dimensional analysis VAV by d. Okay. Because the size of the largest eddies is comparable to the large scales, the fluctuations in these eddies are actually what are called anisotropic. Okay. Okay. I said that at a given location you will have fluctuations in all three directions. However, the intensity of the fluctuations or the root mean square of the velocity in the fluctuations is not the same in all three directions. It is anisotropic. The fluctuations in the flow direction are typically much larger than the fluctuations in the cross stream directions. Okay. This is a characteristic of all turbulent flows, because the flow is being driven by a pressure gradient in the axial direction, and the fluctuations in the axial direction are typically much larger than the fluctuations in the other two directions for a turbulent flow. Okay. What is the size of the smallest scale eddies? Okay. So, the size of the smallest scale eddies is given by what is called the Kolmogorov universal equilibrium, okay, hypothesis. Okay. The idea is that the smallest scales eddies are so much smaller than the large scale flow that the size and the time scale of these eddies does not depend directly on the large scale flow, that is the diameter and the average velocity. Okay. For the large scale flow, obviously you are forcing it on a length scale comparable to the diameter. So, the size has to be the diameter, okay, and the velocity has to be comparable to the mean velocity. The smallest scale eddies in this flow are so much smaller than the large scale flow that they do not directly depend upon the size. They depend only upon the local environment at that particular location, okay, the strain rate and so on at that particular location, not the average, the total size of the pipe. Okay. And what they do depend upon is the dissipation rate, and the to back up a little bit, the Reynolds number based upon the large scale is much larger than 1. Okay. So, the Reynolds number, okay, is rho V average d by mu, okay, is much larger than 1 for the large scales. Okay. We know that for turbulence takes place only at high Reynolds number. Okay. So, the Reynolds number based upon the large scales is much larger than 1. Okay. I will write this for the present as V average d by the kinematic viscosity, because that will be more convenient for me for the discussion. Okay. V average d by the kinematic viscosity. Okay. The Reynolds number we know is much larger than 1. Okay. That means that viscous effects are not important at the scale of the pipe. Okay. Dissipation of energy is not important at the scale of the pipe. Okay. However, for the smallest scales there has to be a dissipation of energy, because whatever energy is being put in at the large scales ultimately has to be dissipated somehow, otherwise one cannot have steady state. Okay. If the energy that is put in is not dissipated, the flow will continuously accelerate. You can have a steady state flow only if the energy that is put in at the large scales is dissipated somehow. Okay. Obviously, based upon the Reynolds number for the large scales, viscous effects are not important, therefore, energy is not dissipated at the large scales. Therefore, energy has to be dissipated at these smallest scales, okay, for the maintenance of a steady state. That is the picture for Kolmogorov universal equilibrium hypothesis. Okay. So, therefore, whatever energy is pumped into the flow due to the pressure gradient across the pipe, that has to be ultimately be dissipated at the smallest scales. Okay. What is the energy put in per unit time? Okay, that is actually the power that is driving the flow. Okay. This is going to be equal to the pressure difference across the end the difference in pressure. Note that minus delta P is positive because the inlet pressure is greater than the outlet pressure times the volumetric flow rate. Okay. That is going to be equal to the power that is driving the flow. Okay. Delta P is a force per unit area, volumetric flow rate is the velocity times the cross sectional area. So, therefore, the delta P into V dot is force multiplied by a velocity. Okay. Force multiplied by a velocity, which is force multiplied by length per unit time, that is a power. Okay. That is a power that is driving the flow. Okay. So, this is the power that is driving the flow, the energy put in per unit time. All that energy that is put in per unit time has to be dissipated, okay, due to viscous dissipation ultimately, because the inertial mechanisms do not dissipate energy. Energy dissipation is due to viscous effects alone. So, this entire power has to be dissipated. Okay. Rather than expressing it in terms of the power, one can express this in terms of the power driving the flow per unit mass. Okay. Per unit mass. Okay. This I can write this as minus delta P into V dot. Mass is the density times the volume, density into the cross sectional area pi d square by 4 into the length. Okay. This is equal to minus delta P by rho L, okay, into V dot by the cross sectional area. This is the power per unit mass. Okay. And this volumetric flow rate per unit area is just the average velocity. Okay. The volumetric flow rate per unit area is just the average velocity. Okay. recall the definition of the friction factor. Okay, recall the definition of the friction factor. The friction factor is equal to minus delta P by L into 2 rho V average square. When expressed in terms of the pressure gradient, this is the fanning friction factor. Okay. Alternatively, this is equal to tau W by rho V average square by 2 if expressed in terms of the wall shear stress. Okay. So, this we had discussed by doing a momentum balance, a force balance across the entire pipe. We had related the wall shear stress to the pressure gradient, okay, and based upon this we got the friction factor. Okay. Therefore, this expression for the power per unit mass, okay, this can also be written as 2, okay, this power dissipation per unit mass can also be written as 2 2 V average square F, okay. I am sorry, I should have a length scale here. So, let me just write that. Okay. 2 rho V average square by D. Okay. So, you recall there was a diameter, ratio of length and diameter in this expression. So, this is equal to this by D into V average. Okay. So, therefore, the power input per unit mass, okay, the power input per unit mass when expressed in terms of the friction factor is equal to 2 not rho V average cubed F by D. So, that is the power input per unit mass whether the flow is laminar or turbulent. What changes is the expression for the friction factor between a laminar and a turbulent flow. Okay. I had sketched out the Moody plot for you for a laminar and a turbulent flow. Recall that for a laminar flow, the friction factor decreases as 1 over the Reynolds number. For a turbulent flow, it does decrease with Reynolds number, but not as fast. Okay, it does not decrease as inverse of the Reynolds number. It decreases much more gently with the Reynolds number. There have been correlations which have expressed this as Reynolds number to the 1/7th power, for example. Okay. There have been correlations which express this as Reynolds number to the 1/7th power, which is a very slow decay. Okay. So, therefore, if we assume that the friction factor is approximately a constant in a turbulent flow, it does not vary very much, then this goes as V average cubed by D. Okay. This is the power input per unit mass, okay, in the flow. This has to be the same at steady state as the energy dissipation rate. Okay, per unit mass. This has to be the same as the energy dissipation rate per unit mass, which is usually expressed by the symbol epsilon. Okay. So, this is the energy dissipation rate per unit mass. Now, back to our discussion on the smallest scales of the turbulent flow. I said that the smallest scales are so much smaller than the pipe diameter that they do not depend directly on the pipe diameter and the average flow velocity, okay, because a small eddy at a particular location, okay, experiences only the velocity at that particular location, not the total fluid velocity, and its length scale is much smaller than the pipe diameter. So, it does not depend directly on the length scale. What it does depend upon is the energy, the power input per unit mass, which is the same as the energy dissipation rate per unit mass. Because ultimately all of the energy that is put in at the large scales has to be dissipated at these smallest scales. Okay. The energy that is put in at the large scales has to be dissipated at these smallest scales. Therefore, the length and the time scale of these eddies has to depend upon the smallest scales, the energy dissipation rate or the power per unit mass that is input. And it has to depend upon the mechanism of dissipation, that is viscosity. Okay. Rather than writing it in terms of viscosity, I will write it in terms of kinematic viscosity, because I have divided throughout by total mass. Okay. So, therefore, basically the Kolmogorov hypothesis states that the length and time scales for turbulence, okay, and velocity scales for smallest eddies depend only on the energy dissipation rate epsilon and kinematic viscosity nu. Okay. Kinematic viscosity is a momentum diffusivity. We know that it has dimensions of length square T inverse. Okay. We know it has dimensions of length square T inverse. What about the energy dissipation rate? Okay, what is the dimension of the energy dissipation rate? Velocity cubed by diameter. Okay, you can see from here it is velocity cubed by diameter. So, this will be length square T power minus 3, where L is the length dimension, T is the time dimension. Okay, so, this is a length square T power minus 3. Okay. So, it can depend only upon both of these quantities, length square T power minus 3, which is the energy dissipation rate per unit mass, and the kinematic viscosity length square T inverse. And from dimensional analysis, it is quite easy to see what are the length and time scales for this Kolmogorov eddies, the smallest eddies. Okay. The Kolmogorov length scale, okay, this is equal to nu cubed whole power 1/4. Okay. You can verify the dimensional consistency of this. This is length square T power minus 3 by I am sorry, length square T power minus 1. Whole cubed divided by length square T power minus 3. The time dimension will cancel out, and ultimately you will have just a length dimension here. Okay. So, just from kinematic viscosity and the energy dissipation rate, you can create one length scale, and that is nu cubed by epsilon. Okay. The time scale for the Kolmogorov scales. Okay. Is equal to nu by epsilon per half. Okay. Once again you can verify this as the dimension of time. Okay. Nu is length square t inverse, epsilon is L square t power minus 3. If you take the half power of that, this is t. Okay. And the Kolmogorov velocity scale is equal to nu epsilon power 1/4. Okay. Once again we can verify that. Okay. Nu is L square t inverse, epsilon is L square t power minus 3 whole power 1/4, which is L t inverse. So, these are the length, time and velocity scales of the smallest scale eddies. Just from the assumption that the small scales do not depend directly on the flow velocity and the diameter, but only on the energy dissipation rate, energy dissipated per unit mass per unit time, and the kinematic viscosity, which is the mechanism of dissipation. So, basically the dissipation mechanism determines what these smallest scale eddies are. What is the ratio of the small scales and the large scales? Okay. So, let us examine that. What is the ratio of the eddies of the smaller scales and the larger scales? Okay. Okay. Lk by d, okay. The Kolmogorov scale divided by the pipe diameter. Okay. This is going to be equal to nu cubed by epsilon times d power 4 whole power 1/4. Okay. And I will use this expression for the epsilon, okay, for the energy dissipated rate, V cubed by d. Okay. So, this is equal to nu cubed by into d power 4 whole power 1/3. Okay. Okay. And this you can easily verify is equal to nu cubed by V average cubed d cubed whole power 1/4. Okay. This is the Reynolds number power minus 1 by 4, sorry, minus 3 by 4 based upon the large scales. Okay. Note that turbulence is at high Reynolds number. Okay. So, we are having Reynolds number to the minus 3/4 is a small number. So, that means that the ratio of the Kolmogorov scale length scale and the pipe diameter is much smaller than 1. Okay. Similarly, you can take the ratio of the velocity, okay, by V average, okay, is equal to nu epsilon by V average power 1/4. Okay. Once again for epsilon I will substitute V average cubed by d. Okay. So, I will get nu V average cubed by V average power 4. Okay. There is a factor of 1/4, there is a power of 1/4. So, it is nu epsilon by V average power 4 power 1/4. Okay. Okay. And you can easily verify that this is equal to nu by d V average power 1/4. Which is R e power minus 1 by 4, because d V average by nu is R e. Okay. So, there is the ratio of the Kolmogorov velocity scales. Okay. And similarly, you can get the ratio of the time scales. Okay. T k divided by the time scale for the large flow is d by V average. Okay. and you can go through the expression once again. I substitute nu by epsilon power half, okay, into d by V average, okay. And you can do the calculation in the same way, and you will get this as R e power minus 1 by 2. Okay. So, what this is showing is that the ratio of the Kolmogorov scales and the large scales is the Reynolds number to some negative power, minus 3/4 for the length scale, minus 1/4 for the velocity, and minus a half for the time scale. Therefore, the Kolmogorov length, velocity and time scales are much smaller than the macroscopic length, velocity and time scales. These are the sizes of the smallest eddies, such that all of the energy that is put in at the large scales is finally dissipated at the smallest scales eddies. So, we will discuss a little bit more about the large scales and the Kolmogorov scales in the next lecture, and then I will discuss how that energy is transported from the large scales to the small scales. I will continue this in the next lecture. I will see you then.